Hi everyone, it's glad to show our work MotionGS here. Our work explores explicit motion guidance for deformable 3D Gaussian splatting to improve dynamic 3D reconstruction. To begin with, let me introduce the problem that MotionGS addresses. The input is a set of multi-view images, which is captured in a dynamic scene using a single moving camera, which is also the most common scenario in our daily life. Our target is to reconstruct a 3D model with realistic appearance and natural motion, which continuously capture dynamic changes over time. In static reconstruction, there are some significant progress in recent years, largely contributed to the emergence of NeurIPS and 3D Gaussians. Subsequently, the following work extended them to the reconstruction of dynamic scenes, mainly using the deformation field. However, this method only used deformation field to represent Gaussian motion, but lack effective constraints. More recently, some methods such as dye point and Gaussian flow have realized this issue and use optical flow to provide additional motion constraints. Motivated by these works, we find two key points in current dynamic 3D Gaussian methods. First, most existing dynamic 3D Gaussian methods simply use deformation field to model Gaussian motion, which lacks explicit motion constraints. Second, compared with using optical flow to supervise Gaussian deformation, we decouple motion flow from optical flow to directly provide explicit motion priors, thus making motion constraints more effective. Our framework is showing the figure. The given input is a set of multi-view images with camera poses. We extract each two frames and send them into FlowNet to obtain optical flow. Then we initialize the 3D Gaussian with deformation field. Given a novel view, it can splat a dynamic Gaussian at a certain time step. Meanwhile, we can use depth splatting to obtain the metric depth. Given the camera poses, we can calculate the corresponding camera flow through geometric transformation. After decoupling motion flow from optical flow, we use this prior to supervise the Gaussian deformation. Finally, to address the potential problem of inaccurate camera pose, we used a pose refinement module to fine-tune the given camera pose. As a result, our method significantly outperforms state-of-the-art methods in dynamic molecular scenes, especially those with rapid movements and high complexity. Additionally, our method also consistently improves performance in wide smartphone captured scenes, despite irregular camera movements and inaccurate poses. Here we visualize all data flows. We use motion flow to supervise Gaussian flow, ensuring consistent and accurate motion guidance. Finally, we provide some video results, highlighting the superiority of our motion modeling. And here is the process of refining camera poses. Thanks for your attention. Please check our project page for more details.